Some properties of acids and bases that you should be aware of are acids have sour tastes. They are proton donors, protons being just H+, so they donate hydrogen ions. They turn blue litmus paper red. While bases have bitter tastes, they have a slippery feel, so a lot of times you see them in cleaning products. They accept hydrogen ions, or proton acceptors. They turn red litmus paper blue, and a lot of times they're going to be used in cleaners. You need to know two different definitions of an acid and a base. The first definition is the simplest one, which is Arrhenius. Arrhenius' concept said that acids produce hydrogen ions in solution, while bases are going to produce hydroxide ions. So HCl would be an Arrhenius acid, because when it's dissolved in water, it's going to produce hydrogen ions and chlorine ions. While NaOH would be an Arrhenius base, because when it's dissolved in water, it produces sodium ions and hydroxide ions. So according to Arrhenius, anything that produces hydrogen ions in solution is an acid, and bases are going to produce hydroxide ions. But this is a pretty simple definition, and so we need a little bit broader of a definition to encompass more acids and bases. That's where the Bronston-Lowry model falls. Bronston-Lowry has to do with protons. It states that an acid is a proton donor and a base is a proton acceptor. So in the reaction below, we can see that H2O and H3O are conjugate acid-base pairs, which means they're separated by only a hydrogen. And then HCl and chlorine are also a Bronston-Lowry acid-base pair. So when we go from H2O to H3O, notice that to go from here to here, it had to have gained a hydrogen. So this would be the base, because it was a proton acceptor. While HCl, to go from here to here, lost a hydrogen. Therefore, it would be the acid of the pair. So the conjugate acid-base pair is simply a pair of compounds that are separated by only a hydrogen. So HA and A, they're separated by only one hydrogen. H2O and H3O plus separated by only one hydrogen. With a conjugate acid-base pair, you have an acid on one side and a conjugate base on the other side, or a base and a conjugate acid. So a conjugate base is everything left of the acid molecule. So in this case, this is my acid. Because of these two, this one has more hydrogens. To go from the reactants to the products, it would lose a hydrogen. This then would be a conjugate base, because in the reverse reaction, A would gain a hydrogen or be a proton acceptor. H2O is the base, because to go from the reactants to products, it would accept a hydrogen. So H3O plus must be my conjugate acid, because in the reverse reaction, it would donate a hydrogen ion. You have to have one acid, one base, one conjugate acid, one conjugate base. And the acid can never be a conjugate acid on the other side. They have to be opposites. So pause the video and try these three on your own. Identify the acid, the base, the conjugate acid, and the conjugate base in each of the following reactions. Restart when you think you have an answer. So first, these two are a conjugate acid-base pair, and these two are a conjugate acid-base pair. Of the purple ones, this one has more hydrogens, so it's the acid, making this one the conjugate base. Of the green pair, this one has more hydrogens, making this one the base. If you didn't get that one, go ahead and pause the video and look at your second one again. Restart when you have an answer. So first, identify my conjugate acid-base pairs. Those two are a pair, and those two are a pair. Of the two, this one has more hydrogens of the red pair, so that's my acid, which means this is my base. And of the green pair, this one has more hydrogens, so then this one is my base. Of the last one, these two are conjugate acid-base pairs, and that's a conjugate acid-base pair. More hydrogens, and more hydrogens of the pair. I'm going to pause the video and label this one acid-base, conjugate acid, conjugate base, and then solve the question. The question says, what is the acid in the reaction? Since all of our answer choices are only one compound, we're looking at the reactants because it doesn't say anything about a conjugate. And so, of the two, this one is your acid. Had they said, what are the acids in this reaction, then you would also have to pick the conjugate acid, which would be this one. So our conjugate acid then is D. This is our acid, conjugate base, conjugate acid, base. These are a little bit trickier. It says write the formula for the conjugate base of HCO3 negative. Well, if I'm writing the formula for the conjugate base, then this has to be an acid, because they have to be opposite of each other. The definition of an acid is it loses protons. So if this loses a proton or a hydrogen, it would only be CO3. And since I've lost a positive hydrogen, the charge should go down by 1. So the conjugate base would be CO3 negative 2. Go ahead and pause the video and try the next one on your own. So now we're looking for the conjugate acid, which means this is a base. Bases gain protons, so it's going to have 3 hydrogens now, which means the charge should go up by 1. So it was negative, now it's neutral. I'm going to pause the video and solve this one. So that's a base. Bases gain protons. So C must be our answer. Just like we had equilibrium expressions, acids have Ka, or acid dissociation constants. A Ka is solved the exact same way as a Keq or a Kp expression or a Ksp. So our equation we have is this. Just like before, we omit all solids, liquids from the equation. So we're going to ignore that liquid. Ignoring the liquid, we have products over reactants, so H3O plus times A negative over HA. Sometimes that equation that's boxed in has water removed from it for simplicity's sake, in which case the equation is written HA dissociates into hydrogen ion and A negative. H3O is the same thing as H plus. The only difference is H3O includes the water, while H plus is the net ionic where water's been removed. So on here, if we used this simplified version, we have H plus times A negative over HA. Either of those are acceptable. But if you're using H3O, then you should have water in your equation. H plus and Cl negative. So our Ka expression would be product, so hydrogen ion fluorine ion over HCl. Go ahead and pause the video and do the next B and C on your own. Restart when you've done B and C. So this is what you should have gotten for B and C. Notice C, no difference, just take away a hydrogen and what we're left with is NH3. D though is a little bit tricky because it looks weird, but we're going to solve it the exact same way. So first we remove a hydrogen, and we're removing that hydrogen from water. So now we're left with 5 waters, and we removed a hydrogen, which means we still have a hydroxide. That hydroxide has a negative charge though, so it's going to bring the charge down by 1, giving us a 2+ charge. So then our Ka expression looks like so. So acid strength. Strong acids, equilibrium lies far to the right. Remember, far to the right means lots of products. Strong acids pretty much dissociate 100%. So they yield a very weak conjugate base, so weak that it's going to be neutral. So if we have lots of products, would we have a large or small Ka? Our Ka would be large since the acid breaks up almost completely, meaning it has lots of products. Large numerator over a small denominator is going to give us a very, very large Ka. This Ka is so large that most of the time you're not going to be able to find it in reference materials. While weak acids do have Kas, because that Ka is going to tell us how much of that acid breaks apart. Equilibrium lies far to the left because very little of it breaks apart. The conjugate base is much stronger than water, but it's still a weak base. And the larger the Ka value, the stronger the acid. But again, it's still a weak acid. So weak acids produce weak base conjugates, while strong acids produce neutral conjugates. What we mean by that is if I had acetic acid, when acetic acid breaks apart, it's going to produce hydrogen ions and it's going to produce acetate. Acetate is acetic acid's conjugate. They're a conjugate acid-base pair because they're only separated by a hydrogen. So if this is an acid, this has to be its conjugate base. That conjugate base is going to be stronger than water. It's going to be a base. While HCl, when it breaks apart, HCl's conjugate is chlorine. So this is an acid, this is a conjugate base. But chlorine is a conjugate base in theory, but it's such a weak base that water is actually a stronger base than it is. So it is referred to as just neutral. So weak acids are going to produce a conjugate base that's actually considered a base, while strong acids are going to produce a conjugate base that is weaker than water. In other words, it's going to be neutral. So given these two pictures, we have A and we have B. A, if we look at before dissociation and after dissociation, we can see that we have none of the acid left. So this would be a strong acid because it's 100% dissociated into hydrogen ion and its conjugate. While in B, majority of the acid is still together, very little of it dissociated. So this would be a weak acid. There's 7 strong acids that you need to know. HCl, HBr, and HI are the only ones that are binary. And then sulfuric acid, nitric, perchloric, and chloric acid. Make sure that you have those 7 acids memorized. So which one of the following acids would produce the weakest conjugate base? Well, the weakest conjugate base would come from the strongest acid. Of these 4, the only one that's a strong acid is A, so A must produce the weakest conjugate base. Go ahead and pause the video and figure out which one you think is the stronger acid of these 2. If you said acetic acid, you are correct. If you said because it has a larger Ka value than HCN's, then that's the reason why. -5 is larger than -10. Since acetic acid has a larger Ka value, more of it's going to dissociate, producing more hydrogen ions. Water can act as an acid or a base. That means it's amphoteric. It can also auto-ionize to produce a hydroxide ion and a hydronium ion. Hydronium ion is H3O+. So if I have 2 water molecules, one, it can produce hydronium and it can also produce hydroxide by taking one of the hydrogens from the other. Because water has its own equilibrium, it has a Kw equation. Kw is the dissociation constant for water, and it's products over reactants. So H2O produces hydrogen ions and hydroxide. If I was writing a Ka expression, I would ignore water because that's a liquid, and so I just have hydrogen times hydroxide. That Kw value is 1 times 10 to the -14 at 25 degrees Celsius. Remember that equilibrium constants depend on temperature. So if we change the temperature, the Kw value would change. Therefore, the concentration of H and OH in a neutral solution would also change. So 1 times 10 to the -14 is equal to H times OH. So if you know the H concentration, you can find your OH concentration. Our Kw is also equal to our Ka times our Kb value, which we'll see in just a second. Ka is the acid dissociation constant, while Kb is a base dissociation constant. So it says calculate the Kb for HCN. So HCN has a Ka value of that value. When HCN breaks apart, it produces hydrogen and cyanide. This is an acid, which means this is a conjugate base. That acid has a Ka value of that value, 6.31 times 10 to the -10. If I want to know the Kb value for this base, because it's a base, I'm going to get that Kb value by doing 1 times 10 to the -14, which is the Kw, over my Ka value. Solving that out, I get 1.58 times 10 to the -5. So that's the Kb value for cyanide. I'm given the Kb, and I want to know the Ka for its conjugate. Kw is equal to Ka times Kb. So it's 1 times 10 to the negative 14th over my Kb. And that's the Ka value. Go ahead and pause the video and do number 3 on your own. Restart when you have an answer. You should have gotten 7.46 times 10 to the negative 10th. And finally, pause the video and restart when you have an answer for this one. So you should have gotten D. All right, finally, the pH scale. pH is equal to the negative log of H, and the pOH is the negative log of OH. P anything is the negative log of it. So pH in water generally ranges from 0 to 14. You can have negative numbers and you can have numbers over 14, but generally they range from 0 to 14. Like we saw a second ago, Kw is 1 times 10 to the negative 14th, and that's equal to H times OH. And the pKw, or the negative log of 1 times 10 to the negative 14th, is 14. Negative log of H is pH, negative log of OH is pOH. So pH plus pOH equals 14. And as the pH rises, the pOH has to fall because they have to equal 14 at 25 degrees Celsius. So it says calculate the H or OH as required for each of the following solutions at 25 degrees Celsius and state whether it's acidic, basic, or neutral. One other thing that we should mention on this page is if the pH is less than 7, then it's an acid. When pH is 7, it's neutral. And if pH is greater than 7, it's a base. These values are only true at 25 degrees Celsius. If you change the temperature, then it may not be that 7 is neutral. Maybe it's 6.5 or 7.5. So we're given the OH concentration. We need to find our H concentration. So we can use our equation. Kw is equal to H times OH. Kw was 1 times 10 to the negative 14th. We don't know the H concentration, but the OH is 1 times 10 to the negative 5th. So dividing by 1 times 10 to the negative 5th, we get our H concentration to be 1 times 10 to the negative 9th. Comparing -5 and -9, -5 is bigger. So that means my OH concentration is larger than my H concentration. If OH concentration is bigger than H, then that must mean that it's a base. When H is greater, then it's an acid, and if they're equal, then it's neutral. Go ahead and pause the video and try the next two on your own. Restart when you have an answer. So our H concentration on B is 1 times 10 to the negative 7th. Since those are equal, then it's a neutral solution. And finally on C, our OH concentration was 1 times 10 to the negative 15th. That means our H is dramatically larger, so that's a very acidic solution. All right, last question. The pH of a sample of blood was measured to be 7.41. So our pH is 7.41. Calculate the POH, the H, and the OH. So our POH, we can use our equation pH plus POH equals 14. So 14 minus 7.41 gives me 6.59. So looking at that, I know that my solution is slightly basic. Doesn't ask it, but if my pH is 7.41, I know it's got to be a base since it's 25 degrees Celsius. To find my H concentration, I use the equation pH is equal to the negative log of H plus. But I know my pH. So to solve that, I get rid of the negative sign. And then to get rid of the log, I have to raise it to the power of 10. So an easy way to remember that is if you're looking for concentration of H, it's 10 to the negative pH. Or if I was looking for OH, it'd be 10 to the negative POH. So 10 to the negative 7.41 is going to give me 3.89 times 10 to the negative 8. And finally, to get my OH concentration, I can either do 10 to the negative POH, or I can do H times OH equals 1 times 10 to the negative 14. I'm going to go 10 to the negative 6.59, so that's a little bit shorter. And so that's 2.57 times 10 to the negative 7. And since I was solving for concentration, the last two should have the units of molarity.